My teammates are Lynn Calloway and Mike Cook. Today I'm going to cover a system overview, go back look at our SSOC, then I'm going to talk about some of the behavior of our system, how it can respond differently different days and based on what's happened before, then talk about the PI results and then conclusions. Here we have our controller. We can send a signal to our motor, which spins the generator, which generates that output voltage, and a transmitter to send back so we can tell what our output voltage is. The block diagram. We got our manipulated input, which is our motor speed, and then our output is a voltage generator. Here's our SSOC. When we first created this SSOC, we have 4 teammates, and if you look on here, we broke it into 4 blocks, so each team member had 4 points that were responsible for generating. And look how each section, they're all nice and linear, about the same, but it shifts up as you go. Like this is one team member, this is another team member, that's the last one. And it jumps from team member to team member. The one I have circled the point, it's 70% motor speed. We have an output voltage of 40%. Here's an example. Go back to this. Here's a point I'm going to show an example of. At 70% motor speed, where we generate a steady output of 41 volts. Here's an example graph I ran for 60 seconds at 70% motor speed, and it came up to around 30 seconds to 41 volts. Here's the same exact experiment ran different time. 70% input speed, and it came up to, after 60 seconds, it's only around 18 volts, but it's still rising. If you let it go on and on and on, it'll eventually trail up to like 25 or 30 volts, but it changes from day to day. So back to our SSOC, the same point that was at 41 could just as easily have been down here, just depending on where we ran it, and same for here. Like, it could have gone up and down depending on what was ran before us.
Interesting.
Can you believe how difficult that would be to control something that varies from day to day? Say yes.
Yes.
That must have been a real challenge for your team. Green, y'all didn't have anything vary from day to day, did you?
Nope.
You run at 50%, it's right there in the, boy. Everybody say, that certainly is interesting, Kevin.
That certainly is interesting, Kevin.
One thing I was trying to figure out why this happened was magnetism left over in the generator after it was run. It goes down after a while if it hasn't been ran for a while. So if you run an experiment right after it's been at 100%, you get a higher output than if you just run it on if nothing's been ran for a couple hours. So I ran the same experiment. Here's an example. I have 3 of the slides showing. But this is an example of a cold start where it's 69% input for 60 seconds. The 3 graphs I'm showing you are all scaled the same. So it comes up to a steady state around 30 seconds and puts 14 volts and will stay there. This graph was ran about 20 seconds after I ran it. I split the generator up to 1 minute, or 100% for 1 minute. And then I ran this graph with I think about 10 or 15 second delay. And you notice how it never reaches steady state, it's constantly rising. And I see that trend every time if you run within like 10 seconds to a minute or so after it's been ran 100%. It never reaches steady state, it just slowly climbs on and on. And here's an example running instantaneously. So if I ran 100% motor speed for 60 seconds, and then 1 second later, it was 69% for 1 minute. And it goes all the way up to 35%. I did this a couple times and tried to plot it, the effect of time. And each one of these points is 69% motor speed ran for 1 minute after running it at 100%. It was kind of, I can't tell exactly when it starts and stops until I go back and look at the data and the experiment, and I can see the completed time. So I couldn't get like set increments on the when the experiments ran. You can see most of the voltage seems like it bled off after about 5 seconds. And then there's still some remaining residual magnetism that bleeds off all the way up to about a minute or 2 or 3 minutes.
What did y'all say just a minute ago?
That's interesting.
It was interesting.
Interesting.
Kevin.
How about saying, Kevin, I don't see how in the world you could control anything that looks like that.
I don't see how you can control anything that looks like. So,
But this whole graph was shot the next day. I got up and ran the same 69% for 1 minute, and it had been, I think, about 4 hours since it had been ran. And this is the graph that was produced. This is scaled differently than my other ones. But notice how it comes up and looks like it levels off way. It just steadily goes up and steadily goes up, and then starts to rise again after about a minute. And this is up to 24 volts, and that's a cold start. So this is the same experiment I ran that should have been steady at 14 volts, and that's where I see most of the time. So I don't, the time effect does have that effect, but there's something else also changing the way it operates from day to day besides that. So I never could figure that out.
Could you put back up? Why don't y'all say, Kevin, if you noticed that in the first week or two, you might have said, hey, this is uncontrollable, forget it.
Right.
Kevin, you noticed that?
bye.
I didn't notice this until I had to go back. I was going to recreate some of our original data, and we kept getting, it was totally different. So I kept rerunning the same graphs, and I kept getting different values. This was my original thought was that everything could be explained by that, but I guess the next day when I found this out, it can't.
So,
I really
everything
don't
can't explain by, everything can't be explained by anything.
No.
Wow, say, Kevin, why didn't you just quit?
I quit.
Kevin, why didn't you just quit?
I would have quit.
Think about green. Boy, if I switch, you know, used to be I'd switch teams in the middle of the semester. I'd have green do the blue and blue do the green.
Wow, that's interesting.
You have any suicides?
So all the modeling.
Thank
we did
God
all
that didn't happen
semester,
to us.
It jumped around and varied, and nothing matched between the model and experiment, because depending on what we ran, the system could behave like this, or this. So if you modeled it like this, and it was behave like that, or if you did the model experiment and all lined up, the next day if you use those parameters, nothing was ever consistent. So a lot of our modeling didn't work. The best method I found right at the end was once we just get a general ballpark and just trial and error, run one, change the parameter, and it comes in and does a move for the better. The proportional interval controller is the one thing we've used that actually produces desired output with no offset.
Say that again.
The proportional interval controller is the.
Say, all right, say, Kevin, this is amazing. You found something that solves all your problems.
Kevin, it's amazing you found something that solves all your problems.
What he said.
This is the typical response when we step up. The output voltage jumps well above our set point, and on the way down, you can never do a complete wind down because it's hard to get the voltage to dip below the set point. It usually just goes straight to it and steadies out. But it goes. We hit the set point every time. Don't have any offset. The PI controller, in conclusion, is the only thing that has produced the desired results. But we still need specific tuning parameters for each range and step, and the direction of the step also, because the system behaves much differently on stepping up and down.